Okay, so this is our molecular model activity that we're doing. And I'm going to make some models with you. So the reason that we're doing this in the first place is because when we draw pictures on paper, they don't necessarily look as 3D as they are for models. So I did all the work first and I sort of drew all the pictures, but they're pretty flat. And we know that molecules exist in 3D space. So this is hopefully going to help you visualize what molecules will look like. So the first things they want you to do are hydrogen, oxygen, and nitrogen. And if you drew those models out properly on your line paper, you'll know that they're all linear. And the reason we know that they're linear without even really drawing a picture is that there's only two elements, two things. And the only way to attach two things together is in a straight line. Like you can't make a shape with two things, you only get a line. So my kids made these little models for me, and each color represents a different element. This is hydrogen, little H on it. So I'm just using toothpicks. You can use marshmallows or something too instead of styrofoam balls, which is what I used because they'd be way more fun. And so this is just hydrogen with like a single bond. That's all. It's pretty straightforward. And if we make oxygen, it's the same. So even though oxygen has a double bond, it's still going to be the same shape, which is why even with double and triple bonds, we don't change the VSEPR shape with double and triple bonds. However, I will let you know that the molecules get closer together. And that's really only because in order to have electron pairs in that orientation, they have to be closer together to form that double bond. So still linear. And then nitrogen will be the same. Will be a triple bond though. So you can try these at home. Obviously the linear ones are pretty straightforward. There's not a lot to them. But once we get into more 3D shapes, this is where making models helps. So that's your triple bond. And again, a triple bond would be even closer. So if I was able to make these closer, this would be the shortest bond because you have 6 electrons that are all sort of within the same close space, and you have to bring them close together to make that happen. Then we get into our 3D shapes. And the first one's methane, or CH4, carbon tetrahydride. And I'm going to show you how you draw it on paper and then show you why that's wrong. So on paper, we draw it like a T. So one to each of the 4 corners in the 2D plane with our hydrogens on each side. And this is all fine when we're, learning chemistry and drawing structures for the first time. But this shape is flat and there's nothing coming out or going in on the other side. So it's all 90-degree angles, but that's not actually what shape methane takes. It takes something called tetrahedral because we need 3D. We need things to come forward and back. So 90 degrees works when it's planar, when it's flat, but it doesn't work so well. So we have to change this a little bit. So usually I pick one and make it the bottom, or sorry, the top. And then I'm going to change my angles up a little. And really all I'm trying to do is just to get them as far away from one another as I possibly can. It's a little bit closer in 3D space. So something like this. It's not perfect. Let's measure it just to see how close I was with angles. Yeah, I'm a little off for this one. This one's about 110. That's actually not too bad. This one is more than 110. So the angles in tetrahedral are 109.5. You can use a ruler. So it's more like a tripod. Okay, this one should be pointed down a little bit more to make it right. Okay, so it's like 3 sort of pointing down in a triangle and 1 coming up straight. And all the bond angles are 109.5. And this is like carbon makes awesome bonds and really strong connections, and this tetrahedral is like the go-to. That's the goal of all molecules. Tetrahedral has the most stable angles. So that's 109.5. Now when we do our next structure, which is nitrogen trifluoride, it's almost the same. This one has 4 bonds and no lone pairs, so 4 things. Nitrogen trifluoride has 3 bonds and 1 lone pair. So still 4 things, 3 bonds plus 1 lone pair. So they both take on a similar shape, but the angles between the bonds get smaller, and that's because lone pairs take up more space than bonding pairs. So it has a similar base, the 1, 2, 3, but here's where your lone pair would be, around here. And so these angles, instead of being 109.5, actually get a little bit smaller to accommodate for the fact that the electrons are pushing them closer together. So typically in a shape like this, we get about 107. So not that much. Again, 107 is approximate because it depends on what atoms there are and everything, but almost the same shape with this sort of invisible lone pair. Still that sort of tripod shape, and that's called trigonal pyramid. And then the next one is water, and hopefully we know what water looks like because probably learned a lot about it in terms of solutions. And again, water has 4 things. It has 2 bonding pairs and 2 lone pairs. So again, it's sort of like a tetrahedral shape. It's actually called bent, but it's got a lone pair here and a lone pair here as well. So it's still sort of like a 3D shape, something coming here and something coming here, but they're just lone pairs. And again, the angles will be a little bit closer together than we would expect in tetrahedral and trigonal pyramid because there's 2 lone pairs taking up a lot of space and moving them together. So we expect bond angles for water about 104.5. So tetrahedral 109.5, trigonal pyramid about 107, and bent for water about 104.5. But they all have 4 things, so they have the same electron geometry. All right. Now we are going to get into exceeding the octet rule. And so you'll learn more about this when you take grade 12 chemistry classes. And so just like here where we were trying to get all the bond angles as far away from one another as possible, if we add in another bond, if we have 5, we're going to be doing the same thing. So I'm going to try just my best to get 5 as far away from one another as I can. And I usually start with doing a triangle. This one shape is going to be called trigonal bipyramid. So it's going to have a triangle, and then it's going to have one coming forward and one going back in 3D space. And this actually has 2 bond angles in the shape. So the top part here, it's hard to show, you can see a 90-degree angle. That's one of them. But the other angle that you see is this angle, which is 120. So this part forms the trigonal part, the 120, like a triangle, and then these angles right here are the 90 degrees. So that's a trigonal pyramid. And trigonal pyramid's the hardest one to know that it's symmetrical, but it actually is a symmetrical structure. It has 2 planes of symmetry that you can cut along. Okay, so that's a hard one to see. That's why drawing these structures or making these structures is good. And then the last one is, and again, you could add the bonds, I'm just going quick, is sulfur hexafluoride. And I use sulfur yellow because sulfur is like a yellow, smelly, gross solid. And for this one, we need 6. So this one actually does get to be that fun 90-degree square. And then I'm sure you can figure out after this where the other angle is going to go. 1 forward, 1 back. So they all follow a lot of patterns. And if you can count the things, whether it's bonds or lone pairs, as long as you know that total, 2, 3, 4, 5, or 6, they all fall under roughly the same shape. So this one is 90 degrees in every direction. Okay. And sulfur hexafluoride is a really cool gas too. If you guys Google sulfur hexafluoride, it's like the opposite of helium. Helium makes your voice go up, but it's denser than air, so it makes your voice go down, and you sound like Darth Vader. So there's lots of YouTube videos like that. It's really cool. So hopefully this will help you a little bit with models, especially when you're trying to talk about polarity and planes of symmetry. It's really hard to see sometimes on paper. We use those like thick triangles and the dashed hatch lines to show forward and back, but sometimes it's just nice like holding the models in your hands. Again, you can just use like popsicle sticks or marshmallows or anything like that you have at home to visually see. Just sometimes it's easier to see holding on to it, knowing why things are polar and non-polar when you get to that part of chemistry. Okay, hopefully this helped. One more I forgot to do is CH2F2. So I'm just going to take CH4 methane and I'm going to just replace 2 of those with fluorines. And the reason I'm doing this is because sometimes when we draw them on paper, we put like one fluorine up and one fluorine down. And other people will put one fluorine on the left and one fluorine right beside it on the side and say that it's a different structure. And you will learn a little bit about something called stereoisomers eventually when you get to talking about organic compounds. But I wanted you to see that even if you drew it on paper and it looks like one up and one down, sort of like that, even if you twist it around, like the two fluorines and the two hydrogens are always going to be sort of side by side no matter which way you put them. So even if I moved this one here, it's still the same structure no matter which way I draw it. Now it will have slightly different properties depending, and it's based on something called chirality. But that's something a little bit beyond the scope of what we're talking about right now. But just know that, you know, if you draw it in 2D and you have one up and one going down, someone will say that's different than one up and one to the side. And it's really not in 3D. It's the same structure.